Now we're looking at differentiation using limits of difference quotients. So now we're looking at when the interval becomes smaller and smaller. Now you can find the slope at a particular point. The slope of a tangent line is given by here, this formula here. The limit as x approaches 0 of f of x plus h minus f of x divided by h. So we're looking at the slope line when the interval becomes shorter and shorter. So now we can find the actual derivative at a point. Okay. So now we're looking at a tangent line which goes through one point. This limit is also called the instantaneous rate of change of f of x at a particular point. Okay. Now the derivative of x is the function f prime, which is defined by f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x divided by h, provided that the limit exists. If f prime of x exists, then we say that f is differentiable at x. That means there's a derivative there at that particular point, x. So now we're looking at the derivative at a particular point that might have changed at a particular point. Okay. This first example here, they ask us to find the derivative at -3 and 4. So we find the derivative of the function first. So the first thing I did was here, I wrote out the formula for the derivative at a point. That was the first thing I did. The second thing I did was here, I assigned values to my variables here. The third thing I did was I plugged into it. I expanded. After I plugged in, I simplified. I expanded x plus h. And I canceled out x squared and x squared. Okay, then I had a common factor of h here, so I factored that out. The h is canceled out. So now I have here 2 plus h. Then I take the limit as h goes to 0. And I have right here 2x plus 0. Okay, that gives you my derivative of the function. Now they want to know what is the derivative at a particular point. So f prime of -3. So I plug in a -3 here. -6. F prime of 4. End up with 2 times 4, which is 8. Another example here. They give for f of x equals to x to the third. They want us to find the derivative of the function and then evaluate it for f of -1 and f of 1.5. So the very first thing I did was I wrote out a formula for the derivative. The second thing I did was I assigned values to my variables that match the formula. F of x plus h. And then I went ahead and expanded it out. Then the third thing I did was I plugged in. And the fourth thing I did was I simplified it here. X to the thirds cancel out. And I got a common factor of h here. So I can factor out the h. The h's cancel out. So I have this function. Now I can take the limit as h goes to 0. So I'll put a 0 there, and they equal 0. And the only thing that's left is 3x squared. So that first derivative is equal to 3x squared. Now they want us to evaluate it for -1 and -1.5. So I evaluated for 1, 3, then I evaluated for 1.5. I get 6.75. Okay, you can see that there. So now they want us find the derivative of the function f of x equals x to the third plus x squared. So the approach I took is that we already found out the derivative of x to the third is going to be 3x squared. We already found out that the derivative of x squared is 2x. Okay. So to find that f prime of x is right there. Okay. And then you want us to evaluate it for -2 and 4. And we get our two values there. Okay, 8 and 56. So they want us to find the derivative of the function and evaluate that derivative at x equal to 2. Then they want, okay, we'll just do the first two parts there. So the first thing I did was I wrote out my formula for the derivative. Second thing here, I assigned values to my variables, so f of it. Then the third thing I did was I plugged into it. So notice here I have my numerator, I have two fractions with different denominators. So I'll rewrite it as one fraction. So I'll get rid of the parentheses, then I can simplify it. 3x minus 3x cancels out. Okay, so now I have this right here. So everything's being divided by h. So divided by h is the same thing as multiplying by 1 over h. Now my h is canceled out, and that gives me the derivative there. So I'll take the limit as h goes to 0. Okay. I end up with -3 over x squared. Then they want us to evaluate it. So there's my derivative there. Evaluate it for f of 2. So I plug in a 2 there for x. I end up with a -3/4 is my answer. Now, when I had those two fractions with different denominators, I got rid of it by using this formula here. Cross multiply there. Let's see here. Well, this one here, they want us to find the derivative and evaluate it. So I found my derivative there, wrote up my formula, assign values to my variables here, and I plugged into it. Okay, these have, I can't combine them to different denominators, so we write them with one denominator. Parentheses, get rid of the parentheses, so those two get canceled out. So everything's being divided by h. So dividing by h is the same thing as multiplying by 1 over h. The h just cancel. Now I can take the limit as h goes to 0 and end up with 2 over x squared. Okay, when it's not differentiable. Well, it's not differentiable if there's a corner at that point. Some functions have corners built into them. An absolute value function. Absolute value function, because it has a corner there. Function not differentiable at a point if there's a vertical tangent. If it's not continuous. It's not differentiable at the vertex. It's because it has a corner there. Okay. Tangent line deals with the derivative of a point. It touches the curve at one point, and then there's how they define the derivative of a function there. Okay. Function's differentiable at a point x equal to a, then it's continuous. That is, differentiability implies continuity. Okay. However, continuity does not imply differentiability. Absolute value function, for example. Okay. Function that's not differentiable at point A if there's a discontinuity, there's a corner or a vertical tangent at that point.